So before we can do anything, we need to think about how we'd like to represent our approximate solution. Ideally, we'd be able to find our exact solution. However, if we're trying a numerical approach, it implies that we don't have an analytical solution that we can use. So the best we can do is an approximate solution that we'll represent with q tilde. We can think of the approximate solution as belonging to some finite vector space. So this vector space must have a set of basis functions or basis vectors that we'll call psi. So in other words, our approximation will be some linear combination of these. So we can see here, here's our approximation, and it's some sum of a coefficient times our basis function. And it's worth noting that it's our basis function that is spatially defined. Our coefficient is just some scalar number. And the linear combination of all these basis functions will give us our approximation for our solution. Now, our choice of m here could be potentially anything. If we'd like to be more accurate, ideally we'd like to make m greater. As m increases, our approximation converges towards the exact solution, with the limiting case being m equal to infinity, in which case it's assumed that the finite vector space converges uniformly towards the exact solution vector space. So we'll choose the vector space in this simple example to be the space of all polynomials of order 1 and less. So in this case, m is just equal to 1. So therefore, we would expect our solution approximation to be linear. So because m is equal to 1, we must have two basis functions, because we start at I equals 0 and m is equal to 1, so we have two indices here that we can cycle through, 0 and 1. So in this case, we'll choose two ramp functions as simple examples that are very easy to work with. Let's see what they look like.